We are back once again for daily LeetCode. It is day 80, a momentous day, merely because it is day 80 and we exist, right? The hyperbolic coding coalition is multiplying by a factor of 45 every day. That being the case, we've had to enlist the help of all the global agencies across the planet so that we can divert resources, or not even across the planet yet, we're not there yet, but diverging resources across the nation to divert resources to the HCC, the Hyperbolic Coding Chamber, which is our Discord, so that we can actually get people to and allow them into the Discord. So we've been close talks with Discord to make sure that if you click the join link in the YouTube description below, right, that you won't enter into a queue that has an estimated completion time of 2 to 6 years. So for a limited time today, if you join the Discord, it'll let you in and you won't have to wait 1,000 years to enter. So you're going to want to join the Discord at all costs before it is too late. That being said, yesterday we were working on some problems, pretty cool problems indeed, right? We had to speed run some problems, but in retrospect, I was doing some thinking, and I think maybe that wasn't the best play, right? We're speed running problems, we're going too fast, right? Ultimately, it was fine for that one day yesterday. I worry that it could be a problem going forward. So it's a tough thing to balance. It is a tough thing to balance. I was listening to a podcast, a Lex Friedman podcast, and this is the episode that he's talking with John Carmack, legendary programmer, human, and person. I don't know too much about him, except I know he did a lot of work with games, and that he's pretty much regarded as one of the greatest programmers to live. And yeah, I've just been watching, osmosising a lot of lessons from that, and I think one of the bigger things I've learned is that we've got to slow down, right? I personally have a big problem with attention to detail, and I think because I spend so much time leet coding, right, and the output is so binary and is so binary, right? Either you get the problem right or you don't, that I think rushing through to make sure that code gets sent in, right, and just clicking run when you can't guarantee that your assumptions are correct, that the algorithm makes sense. It's just a bad habit to get into, and personally, it seems to seep into my other work as well. So it's something we want to fix. So today, we're not going to go super slow, but we're going to do a couple things. We're going to try and verify our assumptions, and at least make certain that the algorithm that we're writing has some semblance of correctness before we submit it, right? And so that's going to be the goal for today. We're still going to aim to go a little bit faster, not faster in the sense that we're going to be speed running, but faster in the sense that I might not, I try and explain it like I was teaching or something. We're still going to do that, but I don't think we have to do that for every single problem. So that is the case. We have some legendary comments as always. Thomas Wong says, "Good job." Good job to you, brother. I tried. Good job to you too, brother. So we're hoping to continue making good progress. And we have a comment from Marcel Monteiro Cruz. Thank you, brother. Let's go. Okay, so we're back once again, and it must continue. Okay, so problems for today. I don't really know what we have today. We just have number of provinces. This is a problem we usually solve in JavaScript. I don't know if we're going to try it in Ruby. I think we could throw one together in Ruby. So we can't always be ready before we try something new. So sometimes it's just going to have to be that way. That being the case, we're just going to jump into it today. Make sure you join the Hyperbolic Coding Chamber as well. We have a lot of new people join recently, and it's been pretty cool just to see like why people are joining and just how they're going about their grind. So that's pretty cool. And so we're just going to jump into it today. I'm a bit short on time, and let's do it. 30 minutes, right? So here we have, I just want to make sure everything's centered. My camera is way too large. So that's better. Number of provinces. There are n cities. Some of them are connected while some are not. If city A is connected directly with city B, and city B is connected directly with city C, then city A is connected indirectly with city C. So I think they're talking about like a transitive connection here, right? A is connected to B, right? B is connected to C, and so A is connected to C, indirectly with C. So they're talking about connectivity here in terms of graphs. A province is a group of directly or indirectly connected cities and no other cities outside of the group. You are given an n by n matrix is connected, where is connected sub I sub j is equal to 1 if the ith city and the jth city are directly connected. So we're being given an adjacency matrix, right? And is connected sub I sub j means there's no connection to the city otherwise. Return the total number of provinces. So let's map this to our problem, right? We have 3 cities, right? 1, 2, and 3, right? And the connection is going to vary, right? It looks like in this case, right, we have a connection between city 1 and 2 and no connection between the remaining cities and 3, right? No other cities outside the group. So a province is a group of directly or indirectly connected cities and no other cities outside the group. So what this problem is really getting at is our connected components, right? So a connected component is basically, I think it's I want to get this right. I think it's basically when we have for a component, basically, right, or a subsection of a graph, is there a path between all the components? I think we have to double check that. Or it's a group of directly or indirectly connected cities and no other cities outside of the group. So if a province is a group of directly or indirectly connected cities, I think what they're saying is that as long as they all share the same parent set, then we should be good. But they're saying a province is a group of directly or indirectly connected cities. So I think what they're saying is a connected component is a group of directly or indirectly connected vertices. And I think is what they're trying to say, right? And since they say return the total number of provinces, they're trying to say return the total number of connected components. So if we look at this here, the total number of connected components is 2, right? And the max number of connected components we can have, right, is the number of vertices. No. Right, actually, I think that is true. The max number of connected components, right, has to equal V, right? Because let's just say we have 3 unconnected, right? None of them are connected, right? Which would mean that we have 3. I think the phrase connected components is very misleading. But I think technically we would have 3 connected components, even though they're not connected to each other. Let me double check this set connected component definition. So we were able to look up connected components, and it's a set of vertices in a graph that are linked to each other by paths, right? So I think we might have phrased this question slightly incorrectly. I think what I'm trying to say is the maximum number of provinces that we can have are going to be, max prov is going to be equal to vertices, right? Because in this case, there's no connection between any of these provinces, or there's no connection between any of these cities. And so what we end up having is the output, which is 3. So our problem here right? We want to be able to count the number of like a set of vertices in a graph that are linked to each other. If a connected component is a set of vertices in a graph that are linked to each other by paths. So when these two is a set of vertices that are linked to each other by paths. I think I see how we can phrase the question. I don't think they're asking for the number of connected components, but I think what they're asking us in a way, they're asking us for the number of vertices, right? Asking us for vertices minus, right, vertices that are part of a connected component, I think. Because imagine if we started with 3, right? If we know the maximum number of provinces can be 3, if we were to iterate through our adjacency matrix and find that there's a connection between these two nodes, right, all that we would have to say, right, is now that 2 is connected to 1, right, then we have one less vertice that is unconnected, right, or that is not part of a connected component. I know how to solve this, but I'm trying to figure out a way to phrase the question in terms of literal graph terminology. But I understand what is being asked. So maybe we can phrase it as vertices minus the number of components, or the number of vertices that are not part of a connected component. We have to check, is our graph undirected? A group of directly, indirectly connected. So we have an adjacency matrix, right? Connection from 1 to itself, 1 to 2. Right? We do have the connection from 2 to 1, right? Because 2 would be the second column, right? And the second column, right, which would be the second array. I mean, the second row, which would be the connections for this vertice here, right, does have a connection to 1. So I think our graph could be directed. So I think another way to phrase the question, I wonder if this would work. If we were to look at this graph, right, we know that if an edge connects two nodes together, then it creates a connected component, right, to some degree. So in another sense, we could phrase this problem as asking for the vertices minus the number of unique edges, right? There's no edges here, so you can have v minus 0, which would give us 3. And then here we could have, right, 3 vertices, right? So at max, we could have 3 provinces. But since there's a connection between these two trees, right, then this one wouldn't exactly work. I mean, this one would work, right? We would have 3 vertices minus 1 unique edge. Actually, I think, and then this would actually work because if we had one more edge, right, from 2 to 3, right, we could say this is a unique edge we've never seen before. Right? Since we've never seen it before, then the total number of provinces is actually going to be 3 minus 2, which would be 1. So let's try something like this, right? We do vertices minus unique edges, right? And if we wanted to do that, we could do it with a breadth first search. I kind of want to use the ADM version. Well, we could still use a regular BFS as well. The problem is the BFS would actually be done since we're using an adjacency matrix. Actually, we don't even have to do that, I think, since we're just counting unique edges. So I think what we could do is, if we iterate, right, if we were to take is connected, right, and grab it out here, let's just say we iterated over it, right? Let's just say we did something like this. This is what our matrix looks like. All you have to do is count unique edges, right? And what we could see, right, is we want to already add an edge for a particular node to itself, right? Because we don't want to include, because in the matrix, adjacency matrix, right, we have technically an edge to ourself, so we have to ignore those. So we just make sure to ignore self connections, and I think we could actually just iterate through the matrix and then keep unique edges, right? And maybe to validate that idea, we could use a set, right? And we could just write this algorithm by hand, right? We'll just say, okay, we'll skip self edges, right? So 1, 1, or 0, 0. Then we have an edge between 0 and 1, right? So in the set, we're going to add 2 nodes, right? We'd add a node called 0, 1, right? We just say we set it to true or something, right? And then we also want to add the opposite of that, 1, 0, because we're only interested in unique edges, right? So then we would subtract 1, right, from our, so we found 1 unique edge so far, ignore self edges, right? And now we're going to try and add 1, oh no, this will now we'd be at node 2, right? And then we'd have an edge to node 1, right, back to itself. We already have it in the tree, so it's not unique, right? So then we would do 1, right? That would be a self edge, right? We'd ignore 0, 0 because there's no actual edge there, right? And then we want to ignore self edges. So I think we could do this, and it is an n by n matrix. So yeah, let's try that. So we'll have a set, which is really just a hash, right? And we're going to say hash.new, and the default value there is going to be false. And then we want to iterate over, right, the matrix, which is going to be is connected. So we'll say 0, right, through is connected dot length dot each do. We'll call this I, right? And then we'll copy this, right? And we're going to shove I back into is connected, right, to get M, right? This is going to be our inner. And so another way to look at this is just row, or the outer one being V, right? Or we can call it X and Y for components, right? We just want to count unique edges. And so we can actually say provinces is going to be equal to is connected.length, and then whenever we find a unique edge, I feel like our spacing's a little off here, but maybe that's not true. I'm just going to return provinces, right? So whenever we find a unique edge, this seems just off. Okay. It's a little off. It's fine. We're just going to do it like this. I think this is actually better because now this lines up better. right? Whenever we find we're going to want to swap is connected with X. Whenever we find a unique edge, we're going to subtract it from provinces, right? And the way we'll do that, we're just going to have a key, right? And so we're going to have a unique key. Or I guess it won't be unique, right? Because it could be undirected or directed, right? But we'll say, right, if we have a connection from one node to another node, right, then the key would just be, you know, X, Y, right? So we could say key is equal to X, Y, and if we say if hash sub key, right, equals false, right, because if it doesn't exist, if it equals false, right, then what we're going to do is add both styles of the key into the hash. So say hash sub key equals true. Then we need one more line, right, where we make that other key, right, where we do Y, right, and X, right, and then we're going to want to do provinces minus equal 1. And so presumably this should work, but let's just double check it, right? We're going to do is connected, right, starting at X, right? We're at column 0, right? I mean row 0, and then we're going to go through the first row, right? So from 0 to is connected sub X, which would be 0, so we have 3 elements. Y is going to start at 0, right? And so this is the other thing we forgot to do. We only want to do this when an edge actually exists, right? And so what we can say is if hash sub key equals false, and if is connected sub X sub Y, right, equals 1, right? So we know we have a 1 there, right? Hash sub key equals false. And, right, like we said, we want to ignore self connects, and we'll say X does not equal Y, right? So we have 0, 0 to start. Does is connected sub 0 equal 1? Yes. X does not equal Y, so we can't do any work here, right? Then we go to 0 and 1, right? As is connected sub 0 sub 1 equals 1? Yes. X does not equal Y? Yes. Hash sub key equals false? Yes. So we do hash sub key equals true. We add 0, 1, and then we also add 1, 0. We say provinces minus equal 1, right? 0 would skip 0, then we'd go to 1. Skip this, we'd have 1, 0. We'd say is connected sub X sub Y equal 1? Yes. Does X not equal Y? Yes. And does hash sub key equals false? No, right? Because we added it earlier. So I think this might work. And I forgot the end. I was expecting an end because we had an unexpected end of input. So it works for this case. Let's see if it works for, I think we're missing a brace. So it works for this one. Let's see if it works for this one. Oh man. Okay. So our output was 0. Right, and here we have a fully connected graph, it looks like. And our output is actually 0. So I think one thing we can do, right, when we have a number of edges, right, that is equal to number of vertices. But I don't know, we have 3 vertices, and we definitely have, if this is basically undirected, since we have a connection between all the nodes, right, we would technically have 3 vertices. What if we had 4 nodes? Then we could have 4 connections or more. So we could have 5 edges. So this actually might not work. If we had 4 nodes, 1, 2, 3, 4, spread out like a square, we'd have 4 unique edges, and then we'd return the number of provinces would actually be 0. And if we had 5 edges, if we had an edge going down the center, then we'd actually return -1. Interesting. This solution is not going to work. So I think what we can do actually is swap this. Yeah, we should have generated more edge cases, right? Because we just ran it for the first 2 cases and it worked. And I think one thing we should try and do going forward is try to generate edge cases where the code wouldn't work. Because this doesn't scale. Another thing we could do is if we do a BFS, a regular BFS, right? We visit 1, right? We visit 2, right? But the problem is, right, we don't know if our graph is fully connected, right? So we need a method of visiting the entire graph with the BFS, and so we have to do a special version of it to do that. But I think the main goal here, right, would be that if we kept a parent array, right, for example, we could have a parent array that just starts like this, right? All the values would be equal to 0 to -1 to start, which means all their parents are themselves, right? And then we could say, hey, we actually found node 2 while being at node 1, because we visit our neighbors during a breadth first search, right? Started at 1, found node 2, right? So now we can say that 2's parent, which is really vertice 1, because we're going to be 0 index, is actually going to be index 0, right? We visit 3, we have no nodes, right? And we end up actually having 2 vertices. So the way we'd actually count this, we'd actually count this by counting, we'd have the number of provinces by counting the number of -1s. Same here for this last one, there's no connections, we'd have 3 -1s. Now what if we consider our previous example with 4 connected nodes, right? Imagine there's a 4th node right here and it connects like a square, right? The parent of 2 would be 0, the parent of 3 would be 1, and the parent of 4 would be 1 as well, right? At least the way we would find them, it would actually be 2. No, not actually, yeah, the way we find them, we'd actually find it like this if we were doing a BFS, which means that the number of -1s, because there would be 1 connected component. So I think let's try that version instead. And if we're going to do that, I think we can reuse some of this. We don't need, we can still use the hash because we don't want to visit nodes we've seen already. So we'll call it seen. I have provinces equal to isConnected.length. Right, and I think to do this properly, we're going to want to iterate over all the vertices, right, in the matrix. So we're going to need an outer loop to do that because we don't exactly know if the graph is connected. So we don't know if we start at node 1, do a regular breadth first search, if we're going to visit the entire graph. So since that's the case, the way we'll know to do work or to do a BFS, right, is when if we haven't seen, if seen, or if not seen X, right, then we want to do some work. Right, and so this is where we could actually have a regular BFS. And like we said, we're going to want that parent array. And that parent array is going to have is connected. We'll just do is connected sub 0. And let's see, is connected always has at least one row. It always has at least one column. So we can say is connected sub 0. Right, dot each for each row, right? Or I guess actually we can just do is connected dot length. Actually, no, we can just do isConnected.each, right? And then do parent.push -1 to set up this array. I'm actually curious to see if the syntax here makes sense. But now we can remove this ignore self connects thing, right? We basically want to do our BFS in here because we want to visit our buddies, basically our neighbors. So to do that, right, you typically have a queue, right? So say Q is going to be equal to X, right? That we're going to say Q is equal to X, right? And if that's the case, we kind of have seen X, right? So now we're going to want to visit the neighbors of X. We can do that by going through 0 is connected sub X. And we're going to have all these components, right? And now we're actually going to know our parents, right? Our parent, the parent of the nodes we visit through Y, or the neighbors of 1, right, are going to be, the parent is going to be X, right? I'm going to say while q.length, I'm realizing now it's not really a BFS, while q.length. Now that I'm thinking about it, we really just need a way to keep track of the parents. So we could simplify this even further. If is connected sub X equals 1, X is not equal to Y, and I kind of want to try something weird where we kind of kept what we did before. We really just want to know who the parents of each node is. And if a node doesn't have a parent, then it would mark a connected component. So let's say while q.length is not equal 0, right? And we actually don't want to say seen X here. We want to do this in the BFS, right? And we'd say cur, it wouldn't even be X, right? It would be cur equals q dot shift, right? Because we're taking it off the front. And so it'd be cur. Right, then we'd go from 0 to is connected of cur, right, to visit our neighbors. These neighbors would be Y. And if is connected sub cur sub Y equals 1, and cur does not equal Y, right, then we can actually skip these two lines. We're going to say the parent of Y is actually going to be equal to cur, and then we can do q dot push Y as the next thing we want to visit. So let's just see if that makes sense. We start at 0, right? Provinces equal to is connected dot length. That means you have 3 provinces. We go from 0 to is connected dot length of 0, 1, 2. So we're going to make sure we visit every vertice. This vertex is going to be X. We haven't seen X before, so Q equals X. then q.length is not 0. So then q.length is not 0, so we're going to pull off x. We're going to say we've seen x before, then visit all of x's neighbors, right, which is going to be 1, 1, 0. And then y is actually going to be the index is connected subcursive. Y is going to say there's a connection, and it's not the connection to itself, so we'd skip this first one. And the parent of y would be cur, so we'd set parent sub index 1, parent to be 0. Then we'd push y, which would be 1. Then we'd go to the top. So y, or we'd visit all of these nodes, right? But is connected subcursive, y wouldn't be 0. I mean, wouldn't be 1, so we'd skip it. Then we'd be at y, when y would actually be index 1. The q isn't empty. Cur equals 1. We visit our neighbors. We have another connection, right, to 1. So we could say our parent of y, because we're visiting our own self, we'd be visiting 1 from 2 would actually give us a problem. Not processed. And I think the distinction we want here, so we'd actually end up visiting 1, again, which would break our parent array. And we don't want to visit nodes we've already processed. So say and processed and we haven't processed y. So we'll have processed equal hash dot new false, and notice process once we visited all its neighbors. And so we'll say processed sub cur equals true. And then I'll put parent just to see. So this does give us the right answer, but this is just lucky because we're not subtracting anything. But our parents array does actually make sense since there's no connections. If we test for our original, then this actually does make sense here, right? Because for our parent array, we have 0, -1, which means the parent of 2 is 1, which is true, right? And we have 2 -1s, which means that's exactly what we're looking for. So then we can just say, right, parent dot each, right, provinces minus equal 1 if, we'll just say parent, right, if p equals negative, or no, if it doesn't equal -1, yeah, if it doesn't equal -1, then we want to subtract 1 from it. Nice. So this is actually pretty slow, but it's interesting because we're technically only doing, we're going to do an n by n iteration over the matrix, right? Because we're visiting every thing is connected dot length, so each, we're visiting every vertice, but we're not going to visit the neighbors, right, if we've already seen it. So we kind of go as far as we can with the breadth first search, and we don't duplicate work if we see a vertice we've seen before. Yeah, I'm interested if we remove the whole breadth first search part and just did the parent part. This could be simpler, but then we do an O of V operation at the end. That would be n by n, and n by n is technically the entire graph, so you could say it's v plus e. So each vertex we do, well, we're going to visit every vertex, and we're going to visit every edge from every vertex, but only if we haven't processed it. That should be v plus e, and then we do an O of v at the end. I think this is linear time. But that is a wrap.